In the previous lecture, we were using L'Hopital's rule, and we primarily focused on the 0 over 0 cases or infinity over infinity cases. And now we have a few more complicated examples just to refresh your memory, right? This was from the last lecture. So we've looked at, right, so I know 0 over 0 was the top case here. We've looked at this type and this type, but there's also these other types of indeterminate forms, 0 to the 0 power, 1 to the infinity power, infinity to the 0 power. These are often used by logs. And then we also have 0 times infinity or infinity minus infinity. So we're going to look at a couple of different cases here. Okay, so when I look at this limit here, so I'm going to just write these out kind of formally in two different things because, again, I don't really want to write 0 times 0. Like, I just want to write them out separately. So if I look at the limit as x approaches 0 from the right, again, we're going from the right, specifically because ln x is only defined for x bigger than 0. So we can't approach ln x from the left. So we can't look at the overall limit. So the limit as x approaches 0 of x cubed, that's just 0, right? And the natural log as x approaches 0 from the right of the natural log of x is, in the last lecture, I really did not leave myself enough space here, did I? Is negative infinity. And so we have a 0 times infinity case. I mean, technically it's negative infinity, but it's still infinity. So we have this case right here. So we have 0 times infinity. And so we can use L'Hopital's rule on this, right? But we need to be able to, it has to be in a fraction. So we need to be able to force it into a fraction that either looks like infinity over infinity or 0 over 0. So like those, the 0 over 0 and the infinity over infinity are the basic cases, and all of these other ones we kind of try to force into that method so we can use it. Okay, so now I have this. Now what can I do here? I do not want to put ln x, so I want to rewrite this as a fraction. To use L'Hopital's rule, it needs to be in a fractional form. So either I need to put this in the denominator or this in the denominator. The easiest thing to put in the denominator, and I'm thinking in terms of doing a derivative of it, because if I put this in the denominator as 1 over x, or the natural log of x to the minus 1, then I have a crazy chain rule. So I'm going to leave the natural log of here, and then to force this down in the denominator, I'm just going to put 1 over it. So 1 over x cubed. Because if I inverted, right, if I multiplied the top and bottom by x cubed, I get the same thing. So this is this just in a different form. So now when I go to look at as x approaches 0, now I know that this is already an infinity case, and now when I plug in 0, I get 1 over 0. So now I have an infinity over infinity case, which means, yes, I can use L'Hopital's rule on it, okay? All right, so let's do that. So we're going to look at the limit as x approaches 0 to the right, and I'm using L'Hopital's rule here, so I'm going to give myself a little note. So the derivative of the top is 1 over x, and then let's rewrite this x to the minus 3 as a nice way to do the derivative. So this would be negative 3 x to the negative 4, so this would be negative 3 over x to the 4th down here. All right, so now before I want to start plugging in zeros here and seeing what I've done, I'm going to simplify my algebra here. So I'm going to multiply the top by x to the 4th over, actually negative, right? And this by x to the 4th over 3, also negative. So then when I multiply these two together, I get 1. And when I multiply these two together here, I'm going to get the limit as x approaches 0 of, let's see, I have negative x to the 4th over 3x. Now I can simplify my x's because I still technically have a 0 over 0 case, but I don't need to use L'Hopital's rule for that because I can just simplify. So this is really equal to the limit, oops, I forgot my from the right, x approaches 0 from the right of negative x cubed over 3. And now there's nothing wrong with me plugging in the 0 because I don't get 0 in the denominator. So this just gives me a 0. Right? So my limit overall is, in fact, 0. All right, next one. All right, so I have x times cotangent of x, okay? Now we saw in the previous thing, we have to be careful about our assumptions. So let's make sure that we have a thing that L'Hopital's rule applies to. So we'll do the limit as x approaches 0 of x. We know that that's 0, but let's say we're going to look at the limit as x approaches 0 of cotangent of x. So instead of cotangent, it's easier for me to evaluate if I think of it in terms of cosine of x over the sine of x. Now when I plug in 0 here, I get 1 over 0, which means this is an infinite case, right? I really cannot make infinities today, or just whatever, okay. So basically this is a 0 times infinity case. Really struggling. There, maybe that's a little bit better. I can finish my case there. And that is the same case that we had up here, right? Which is definitely falls into using L'Hopital's rule. All right, so in this case, I have two different options in this case. Now, normally, we never put natural log of x or something really complicated in the denominator. Usually what we put it down in the denominator is like if we have a leftover x. So I actually have two options, and both of them work the same, okay? So either I could write this as the limit as x approaches 0 of cotangent of x over 1 over x. Now I can do the derivative of the top and the bottom because now I have an infinity over infinity case, right? I can also, in this case, it doesn't really matter because if I put cotangent in the denominator, that's really tangent. So I can look at the limit as x approaches 0 of x over tangent as well. Okay. So this is actually the easier one to do, but this one also works too, so I'll do it both ways. So let's apply L'Hopital's rule. I know that if I put in 0 here, I get 0, and tangent of 0 is also 0. So this is a 0 over 0 case. Now, it doesn't matter that this is infinity over infinity. L'Hopital's rule still applies. So if I use L'Hopital's rule on this one, I take the limit as x approaches 0 of 1 over secant squared x. And I know that secant is built out of cosine, so this is really 1 over cosine. So when I plug in 0, this is 1. So I end up with 1 over 1, and my limit is 1. Right? So now if I continue on in this path up here, I'm going to get, it's a little bit more complicated derivative. I like tangent better than cotangent. But if I take the limit as x approaches 0, I've already said it's an infinity over infinity, so I can use it. So the derivative of 1 over x is negative 1 over x squared, right? That's me using x equals x to the minus 1 as a power, multiplying down the power, subtracting 1, and then I'm just writing it like this. Now the derivative of cotangent is negative cosecant, oops, I wrote that wrong, cosecant squared x. I wrote the two c's together instead of CSC. Okay, so now what do we have? Okay, so I don't like cosecant squared. So let's think of this instead as a limit as x approaches 0. Actually, I did use L'Hopital's rule up here, so I should mark it. So I'm going to write this as negative 1 over cosecant is really sine squared. And then this is negative 1 over x squared. And so my negatives are going to cancel each other out. And when I invert and multiply this, I'm really going to get the limit as x approaches 0 of x squared is going to end up on top, sine squared is going to end up on the bottom. Right, now I have another, so I have another 0 over 0 case. Right? So I can use L'Hopital's rule again. So now I have the limit as x approaches 0 of 2x over 2 sine cosine of x. So now my 2's will cancel, and I really have a limit as x approaches 0 of x over sine of x times cosine of x. Now really up here, when I saw the x squared over sine squared, I knew that this is x over sine times x over sine, so I could kind of see that it should be 1 in the end. Just like, I mean, it should be 1 because I proved it was 1 in the other case as well. But really, I still have 0 over 0 here. Okay, So I could also see, I could stop pretty much at any time because I know that that limit is 1 times 1, which is 1. But if I don't see it, I could use L'Hopital's rule one more time and go crazy. So I have L'Hopital's rule again, limit as x approaches 0. This time the derivative of x is 1. In the denominator, I need to use the product rule, which means I'm going to have, if I do the derivative of cosine first, I will get sine times negative cosine. Actually, sine times negative sine, which will be negative sine squared. And then I will get the derivative of sine, which is cosine, times cosine, so I get plus cosine squared. And finally, I can now plug in 0, and I don't get 1 over 0 or 0 over 0. And in fact, the 0, this becomes 0, but then this becomes 1, so I do get 1 over 1. So sometimes it does matter. So if sometimes you get a little bit more complicated, maybe you want to try and see, hey, could I have moved that other thing? Okay. All right, so we did those. All right, so let's look at another one. Okay. So in this particular case, now, I have the limit as x goes to infinity of x to the 1 over x. So if I think about this, really, then I have infinity to the 1 over x. Now the limit as x goes to infinity of 1 over x is 0. So essentially, this gives me a 0, or an infinity, to the 0 power. And that is, in fact, one of my indeterminate forms. Let me write this again, 0. So infinity to the 0 power. And I kind of gave a hint here that we can also, usually this is evaluated by taking the log and applying L'Hopital's rule to it, okay? So just like, when we were doing the derivative of this x, when we have a base that's a variable and the power is a variable, we need to use natural logs, okay? So we're going to write this one out a little bit more carefully because we need to alter it. So we're going to say that y is equal to x to the 1 over x. And then I'm going to take the natural log. So this is kind of like logarithmic differentiation, but I need to pull this out of here and say, okay, well then this is y is equal to this. So that means the natural log of y equals the natural log of x to the 1 over x. Now in the end, because I can use this for L'Hopital's rule, this was one of my indeterminate forms, I need to force it into some sort of fraction so that I can use my L'Hopital's rule on it. So hopefully I can force it into infinity over infinity or a 0 over infinity, 0 over 0, sorry. Okay, so now I can pull down the 1 over x. So I have the natural log of y is equal to the 1 over x times the natural log of x. And now I see that this is in fact a fraction. So I have the natural log of y equals the natural log of x over x. I want to write it as a fraction. All right, so now I'm going to take the limit of both of these sides. So the limit as x approaches infinity of the natural log of y is equal to the limit as x approaches infinity of the natural log of x to the x. Right, so we started out with y, right? So we're going to have to go back to y. So we're going to first work with this limit. So we're going to kind of just ignore this one and just write what we can do here. So this would be also equal to, so this is an infinity over infinity case, right? Because natural log of x goes off to infinity. The graph of natural log of x looks like this, right? So it keeps rising. So as x approaches 0, right, then I get negative infinity. As x approaches positive infinity, then I get positive infinity because it keeps growing. It grows slowly because it's a log function, but it does keep growing. So this is infinity over infinity case. There, my infinities look a little bit better there. So we have an infinity over infinity case. So I can use L'Hopital's rule. So I'm going to L'Hopital it and say the limit as x approaches infinity. So the derivative of natural log of x is 1 over x. The derivative of x is 1. So now I have the limit as x approaches infinity of 1 over x. And we've done this before. Whenever I plug in infinity, if I have a constant divided by infinity, this is 0, okay? So now, remember, this is equal to this. So I have the limit as x approaches infinity of the natural log of y is equal to 0. But we didn't want the natural log of y. We want plain y because y was equal to our original function. So to get rid of the natural log, we're going to exponentiate both sides. So we're basically going to raise each one of these sides to this power. So really, right, when I take this, the e to the natural log of y basically just gives me my y back. So basically I have the limit as x approaches infinity of y is equal to e to the 0 power. So now I have the limit as x approaches infinity of y is equal to 1, right? So that is, my y was this thing, so now in the last step I can say the limit as x approaches infinity of x to the 1 over x is also equal to 1. Right? So that's using kind of logs like we did with the derivatives. It's just that this time we're taking the limit. We still need, when I have a base and a power, I'm still always going to need a log, okay? All right, so I'm going to do one more, a little bit more slightly complicated case. And this one is actually, if I look at it, I'm going to get, if I look at the limit as x approaches infinity on the inside, I'm going to get, this I know is 0, right? So I'm going to get basically 1 and then to the infinity. So this is a 1 to the infinity case, which is also in here. Whoops, let me make it right side up. Okay, so it's a 1 to the infinity case, and this is often can be evaluated by taking the log and applying L'Hopital's rule. So we're going to do the same thing here. Now, maybe some of you might recognize this as the definition of something that we use sometimes. I'm hoping that you do, but I'm just going to prove this, okay? So if you don't know what I'm talking about, you'll figure it out in the end, okay? So I have a base that includes an x raised to an x power. I know I'm going to need logarithmic help, so I'm going to redefine this function as y is equal to 1 plus 1 over x to the x. Take the natural log of both sides. When I do that, I'm going to bring down the x in the same step, so I have x natural log of 1 plus 1 over x. Okay, so, I mean, really what I have here, I could also think of it like this right now, right? And so when I take the limit as x approaches infinity here, that's the same as the limit as x approaches infinity here. And since all the x's are up here, we can just really put the limit up here. So we're going to put this up here, but then when we come back, we have to remember that this is the power on e. So let's just look at the limit as x approaches infinity of x times the natural log of 1 plus 1 over x. So as I go to infinity, this becomes infinity, right? And then this one becomes 1. So I have 1 times infinity, which is also an indeterminate form. Now, a lot of times whenever I have the 1 to the infinity, right? Actually, though this is, I'm sorry, this is infinity times 0 because the natural log, I don't know what I was saying. So the natural log, this becomes 0, and I get the natural log 1, which is 0. So then I have infinity times 0. So I still have a L'Hopital's rule indeterminate 0 times infinity case. So I still need to force it into some sort of fraction. Now I don't want to put my ln down there in the denominator because the derivative of that would just be awful because then I would need to use the chain rule another time as opposed to the time that I needed already. So I'm going to use the x and shove it in the denominator as 1 over x. So this is the same form, it's just the same equivalent equation, it's just written in a different form. So now I have the limit as x approaches infinity of this. Now I haven't used L'Hopital's rule on it yet, I'm only just putting it in a form in which I can use it. So now I have the natural log of, so I have a 0 over infinity case, okay? But we're going to proceed. All right, so now let's see. Actually, no, I'm sorry, we have a 0 over 0 in case because when I put in infinity here, I get 0 over 0 case. Okay, so we're going to do the derivative of the top and the bottom. Now this gets a little bit messy. So the limit as x approaches infinity. So the denominator is the easy part, so that's negative 1 over x squared. The derivative of this, remember the natural log, the derivative of natural log is always the 1 over the thing times the derivative of the thing, right? So this is 1 over 1 plus 1 over x times, then the derivative of the inside, the derivative of 1 is 0, and the derivative of 1 over x is the same as this 1 over x, so it's negative 1 over x squared. Ah, how beautiful. I have it's all multiplication, and these are exactly the same, so I can cancel them, right? Multiplication, I can do that. Addition and subtraction, I cannot. Right, so now I have the limit. Actually, I should have written, I did L'Hopital's rule here. So the limit as x approaches infinity of the simplified version is 1 over 1 plus 1 over x. And now, when I take the limit as x goes to infinity, this goes to 0, right? And so I end up with 1 over 1, which is 1. Now, remember that I was doing this limit here, right? So this limit here was equal to 1. So basically, I have e to the natural log of y, limit as x approaches infinity, is equal to e to the, remember this whole thing we just showed was 1. So we have e to the first. Oops. All right, so I have e, right, that's from here. E to the ln y is equal to e to this power. And when we did the limit of this whole thing, we ended up with 1. So now we have the limit as x approaches infinity of e to the ln y is equal to 1. And I know that e to the ln y undoes itself. And so basically I have the natural limit as x approaches infinity of y is equal to e. And our original y, we said, was this. And so this is the limit as x approaches infinity of 1 plus 1 over x to the x is equal to e. This is the definition of e. So just a heads up for when you get into Calc 2, if you're going to take Calc 2, essentially any time that you look, I find that most of the time if I look at this thing and I see, oh, I have basically 1 to the infinity, I'm going to end up with my limit being something to some version of e, okay? So that's my end of my L'Hopital's rule lecture and also my proof of the definition of e.